Hi everyone, and welcome to the second lecture in A-model topological string theory. Melissa, please go ahead.
Oh, thank you very much. Yes. So today I'll give my second lecture on A-model topological string theory. Since the first lecture was a week ago, let me start with recalling briefly recalling what happened in the previous lecture. So recall that, so last lecture was an introduction to Gromov-Witten theory, which can be viewed as a mathematical theory of A-model topological string theory. So recall the setup in lecture 1 is we have a non-singular projective variety over the complex number, just a projective manifold, complex projective manifold. And for each gn, which are non-negative integers, and beta is a effective curve class, which is in particular in a second homology class. So we define the moduli space of GNA GM pointed degree beta stable maps to X. So we define this, and this is the Lingman, usually singular proper Deligne-Mumford stack. And recall that, so given a point in this moduli space, so it consists of a domain curve, which is a nodal curve C of genus G, with n distinct smooth mark point, together with map U from the curve to the target X. And we have the forget map. We have the forgetful map, forgetting the map U, and we get a pre-stable curve of genus G and M mark point, and then we stabilize, we get a stable curve. So when we stabilize, we contract some unstable component. We call the map to M bar GMP. So we have this. Also recall that over M bar GNX beta, we have a line bundle Li, one for each mark point. Oh, sorry, this is a cotangent line at the isomar point, and the psi class is the first chain class of this Li. So similarly, we can define this Li on M bar Gn, and the pullback of Li is not the same as Li. So we call the pullback class psi I bar. So this is our second cohomology class with rational coefficient on the moduli space. And recall, we also have, for each mark point, we have evaluation map at the isomar points. So now, so with all the setup, so I think the last thing we introduce is the following. We introduce these correlators. So given gamma 1 to gamma n, which are cohomology classes. Okay, on this page, for simplicity, let's say they are even cohomology classes. So we don't need to worry about the sign when we commute them. And so then let A1 to AN be non-negative integers. We define the descendant Gromov-Witten invariance by we pull back this cohomology classes gamma I by the ICE evaluation map, and then we also take the psi I to the AI's power. So these are rational numbers in general, and they are descendant Gromov-Witten invariants, defined by integrating against the virtual fundamental class. So here the virtual fundamental class is a homology class of degree 2 times the virtual dimension of the moduli space. Similarly, by replacing psi by psi I bar, we get the definition of ancestor Gromov-Witten invariance. Oh, in particular, if we don't have any psi classes, these are known as the primary Gromov-Witten invariance. Okay, so I think this is the last thing we did last time we introduced this invariance. Yeah, so today, the first half of today, I'll continue to review Gromov-Witten theory. Yeah, and the second half, I will talk about the algorithm of the topological vertex. So this is a review, and the plan today is first to oh yeah, so here is just repeat. So in the primary case, if gamma I is a Poincare deal of say some non-singular closed subvariety of codimension ki, and such that the sum of ki is equal to the virtual dimension, then this is a virtual count of curve G in degree beta such that xi passes through the cycle zi. So then the Kontsevich-Manning axioms are axioms about ancestor invariance. So recall that we have the projection with m bar gn x beta all the way to m bar gn for getting the map and stabilize the domain curve. This virtual fundamental class gives us like virtual push forward, which decrease the dimension by like the relative dimension. So P is not actually a smooth vibration, but suppose that it's a smooth vibration, the expected dimension of the fiber is like the virtual dimension of m bar g xp minus the actual dimension 3g minus 3 plus m. So more precisely, if you give like degree alpha, degree k cohomology class alpha on the modular of stable maps, and we cap it with the virtual fundamental class, and we get a homology class of degree 2 times the virtual dimension minus k, and we can just push forward. Now we get the homology class on m bar gn q on m bar gn, but m bar gn is a smooth orbifold, so there's a Poincare duality over rationals. Yeah, so that's the virtual push forward. And so the virtual push forward satisfy the projection formula. So recall that we have a map from m bar gn x beta to m bar gn for getting the map and stabilize the domain. The virtual fundamental class on m bar gn x beta actually gives us a virtual push forward from the cohomology. So from the cohomology of m bar gn x beta to m bar gn. And so this decrease the degree by the relative virtual dimension, which is equal to the virtual dimension of m bar gn x beta, which we denote by d upper x lower g m beta, minus the actual dimension of m bar gn, which is 3g minus 3 plus n. So this is the virtual push forward. So it's given by the following. So first we take any degree k cohomology class on moduli of stable maps. So we cap it with the virtual fundamental class, we get a homology class of this degree. And then we apply P lower star, we get a homology class of the same degree, but now it's in M bar G on M bar Gn. And M bar Gn is a smooth orbifold. So we have Poincare duality. So this, by Poincare duality, we have, the Poincare duality via the actual fundamental class, we get the cohomology class of this degree. Okay, so and then, so this push forward, virtual push forward satisfy the projection formula. If you have alpha, which is a cohomology class on the modular stable map, and then you top it with a pullback of some cohomology class on M bar Gn, and we have this. Okay, so we are going to, so this is the Kontsevich-Manning Gromov-Witten class. So in their paper is denoted I, and the target is called V. So we will use omega. So we define omega upper X, lower Gm beta. So this will be a map from the nth tensor product of the rational cohomology of the target X to the cohomology of M bar Gn. So if we take gamma 1 to gamma n, which are cohomology classes on X, so we like pull back via evaluation map. Oh yeah, so I guess on this page, we do not assume gamma I is like even degree. So we need to, we need to order it in the same way. The order matters. So we pull gamma I via evaluation map, and we get cohomology class on the cohomology classes on the moduli space of stable maps, and then we do push forward to get a cohomology class on M bar Gn. And then if you, so now this omega, so now we get this cohomology class, and then we can take the cup product with the, say, psi classes on M bar Gn. And then integrate and because the Poincare duality is defined by the by the fundamental class of M bar Gn, and also because virtual push forward satisfy the projection formula. So this integral is the same as this descendant Gromov-Witten invariance. So now, so Kontsevich-Manning, so this Kontsevich-Manning axiom, is stated in terms of this Gromov-Witten classes, but they are the same as ancestor Gromov-Witten invariants. So first, so the following definition is the effective. So this is that means that this is zero if beta is not effective, meaning that there's no stable map with this homology class. So that is clear from the definition. And Sn co-invariance. So if we have gamma I, so now we don't assume they are like even of the even degree, but let's assume each gamma I is homogeneous of degree Ki, and we take some element in sigma in the permutation group. And then if we permute the order of, we permute the order by this by the sigma, then we get a sign. The sign is exactly given by by like permuting the order of gamma I in the cup product in the cohomology ring of the target X. And then, so the grading axiom is because, yeah, so comes from the, yeah, we have seen that the degree of the virtual push forward. Oh, so the fundamental class, so let's assume 2G minus 2 plus n is greater than 0, so that there is at least one G m-pointed stable curve. And that's the same as saying that G comma n are not one of these 4 cases. So in this case, m bar Gn is not empty, and we have a we can forget the last mark point, and we get this map. And then so the fundamental class axiom says if we pull back, oh yeah, actually I yeah, so there should be omega gm gm beta. I forgot the beta. So if you pull back omega gm beta via this pi, so in the last component, you add the unit of the cohomology of the target X. And for the omega 03 beta, so it is 0 if beta is not equal to 0, and it is a pairing gamma 1, gamma 2. Yes, so the divisor axiom says the following. So we so again, assuming 2G minus 2 plus n is greater than 0, so we get this forgetful map given by forgetting the Lexmark point and possibly contracting some unstable element. And there's a push forward map, yeah, because we have map in homology, which preserves the degree. Pi induces map in homology, which preserves the degree. And using Poincare duality, we have push forward of like cohomology class, which decrease the degree by 2. If so then the divisor axiom says that if we take the Gromov-Witten class where the last one gamma m plus 1 is a degree 2 class, and then so it is equal to the right hand side. So it's equal to apply the Gromov-Witten class to gamma 1 tensor up to gamma n, and with the factor, which is the pairing of the curve class beta and gamma m plus 1. Yeah, so we should think, because this pi is pi can be identified with the universal curve over m bar gn. And this, yeah, so this map is integration over the fiber. So we also have mapping to a point. If beta is, so this is about the case where beta is 0 and it's a stable stable map which are constant. So it's just a stable pointed curve together with a constant map. So actually last time we talked about we have this identity. Sorry, we have this identity which says, which relate so we recall that last time we have seen that. So if you have a stable map of degree 0, it's just of genus G, and marpoints is just a constant map. So it's a product M bar Gn cross X. This is smooth Deligne-Mumford stack, but the difference of the virtual class and the actual fundamental class as a smooth Deligne-Mumford stack is this, like the Hopchan class of this tensor, exterior tensor of the dual of the Hodge bundle on M bar Gn and the tangent bundle on X. So basically, so the axiom about mapping to a point or constant stable maps, is a consequence of this, and I won't write down the statement for positive genus, but for genus 0, so we don't have this factor and the virtual class is equal to the actual class. And then we have sorry, so we have this, this is so in genus 0 is simply this identity. So the interesting, this is the gluing is relating, before we can state this axiom of gluing, so let's take some basis of the rational cohomology of the target X. And then, so the pairing, the Poincare pairing is non-degenerate. This pairing is non-degenerate. And so let G upper AB be the inverse. Then the diagonal in X, the Poincare deal of the diagonal in X cross X is given by this. So there are two cases. So first, so let's consider a map from M bar G minus 1 and plus 2 to M bar Gn. The image is a divisor in M bar Gn. So you take the last two mark point and glue it, identify it so that you create a node and increase. So this decrease the mark point by 2 and increase the genus by 1. And so I draw a picture where G is equal to 3 and N is equal to 1. So then this says that if you so if you pull back the Gromov-Witten class from M bar Gn with input gamma 1 to gamma n, and this is equal to this. Okay, so it's equal to, so then the pullback to M bar G minus 1 M plus 2 is given by this formula. So if you count another type of the divisor in M bar Gn is is image of the following map. So you can consider your x1 to x. So it's given by, so there's a codimension 1 stratum. So if you consider the so you have x1 to xn MR points, and you consider, like, you split you take I1 and I2, which are subsets of 1 to n, such that their disjoint union is 1 to n. Let ni be the size of ii, so n1 plus n2 is equal to n, and g1 plus g2 is equal to g. So there is this dimension 1 stratum, so where the generic point is given by so it has two irreducible components. Each irreducible component is of genus G1 and G2. And then we take the set in, like, the xi correspond to I sub I is on the first component, and the other mark points is on the second component. Yeah, so this is the image in this map from M bar G1 N1 plus 1 cross M bar G2 N2 cross plus 1. And again, so if we pull back the Gromov-Witten class on GM beta with input gamma 1 to gamma n, so we have the following sum. So first, there's also this epsilon, which so because the epsilon is correspond to, we permute the order of the MR points, such that so the indices in I1 is the first. We move the indices in I1 to the front, and then we need to include the sign coming from this permutation. And because the class the effect, so the degree of the map is, if the degree of the map is beta, then this degree can be distributed to the two irreducible components. Yeah, so we have a sum like B1 plus beta 1 plus beta 2 is beta. And then we have a sum over AB. Yeah, coming from, but basically, if we want to glue two stable maps of genus G1 N1 beta 1 and G2 N2 beta 2, or G1 N1 plus 1 beta 1 and G2 N2 plus 1 beta 2. So when we glue it, we can glue it if the evaluation map at the last mark point is the same point in the target, so that we can glue them to form this map from a nodal curve. Okay, so these are the axiom for ancestor Gromov-Witten invariants. So next I will discuss the axiom for descendant Gromov-Witten invariants. Suppose that GM beta is stable. That means either beta is not equal to 0 or 2G minus 2 plus n is greater than 0. We have this map from M bar GM plus 1 x beta to M bar GN x beta for getting the last mark point, and possibly contrast some component if necessary. So this can be viewed as the total. This map is also can be identified with the universal curve over M bar GN x beta. So then we have some equation involving, so for example, so the string equation says the following. So if we have this descendant Gromov-Witten invariance, where the last insertion, we don't have psi class and we just insert one. And then this can be reduced to an integral over m bar g and x beta with one less mark point. So this sum from 1 to n. So since like the virtual dimension of m bar g and x beta is one less, so we need to integrate some cohomology class with one less degree. So for each, so there's a sum from 1 to n. So you decrease the degree of the psi class by 1. All right, so in particular, if your integral is just some primary Gromov-Witten invariance where the last insertion is the identity, then then we just get 0. So the second thing is the dilaton equation. So it's a last insertion is just a psi class, but the cohomology class is just the identity or unit in the cohomology ring. And then this is so then this, when we forget the point, we introduce the degree of 2g minus 2 plus n. So 2g minus 2 plus n is like the degree of the log canonical line bundle over a GM pointed curve. So the third is the divisor equation. So this is about when we so suppose that last insertion, it's a degree 2 class. In particular, the Poincare dual of a divisor class is a degree 2 cohomology class. So it's called the divisor equation. And then the idea is still like we think this map as integrate over the fiber. And then, so then we have this factor, which is a pairing of the second cohomology class and beta, which is the degree of the map. But also but that's the intuition. But then we also have the second line. Oh. Yeah, so this comes from the fact. Yeah, so this line comes from the fact that if you consider the psi class on M bar Gn x beta and bar, the pullback is not exactly the psi class on M bar Gm plus 1 x beta. There's some discrepancy. And if we study that discrepancy, we get this. So in particular, if so for primary divisor equation, we don't have the second line. And also recall that in the previous section, we also have a divisor equation. And that divisor equation is about ancestor. So, but for the ancestor, since all the ancestor invariants are defined by psi I bar, which is the pullback of psi class from M bar G. Yeah, sorry, let me, so this is not quite, yeah, let me erase this, sorry. Okay, yeah, let me just stop it here. So this is the review of the axiom satisfied by the ancestor Gromov-Witten invariance and descendant Gromov-Witten invariance. Okay, so before I start to talk about the topological vertex, I would like to introduce equivariant Gromov-Witten invariance because so topological vertex is about Gromov-Witten invariance of a toric labial threefold. They are always non-compact. And so far, our definition assumes that the target X is a non-singular projective variety. So let's consider the equivariant Gromov-Witten invariance. I will start with a more general setting. So suppose that we have an algebraic group acting on X. Then the group action on the target will induce group action on the moduli of stable maps. Like each element, which group element will give us an automorphism of the target X, and we can compose a stable map with any automorphism. So we see that G action on the target induces G action on moduli of stable maps. And then this map we introduce like projection given by forgetting the last mark point, evaluation map at the ith mark point. So these are actually G equivariant maps. And also, it is also possible to make this line bundle G equivariant. So if we take the first chain class, now they will be in the G equivariant second cohomology with rational coefficient. So let me give a brief review of equivariant cohomology. But this review, I will actually do it in the, using algebraic topology. I hope it's okay. So let's go to like more general setting, like in algebraic topology. So G is some Lie group. It acts on some suppose that it acts on some contractible topological space continuously and freely on the right. And we quotient by the free action, and that's BG. So so this BG, so then EG over BG is a principal G bundle, and the base BG is the classifying space of principal G bundle, and the total space of is the universal principal G bundle. And they are defined up to homotopy equivalence. For example, when G is C star, so let's first, you can think it as the following. So first, let capital M be some large but still finite number. So C star acts freely on Cn plus 1 minus 0, and the quotient is Cp capital N. So now when you have finite N, then this is Cn plus 1 minus 0 is not contractible. But when N goes to infinity, this will give you, give us the universal bundle, universal C star bundle over Cp infinity. So the universal C star bundle over Cp infinity, you can think as it's the frame bundle of O minus 1. So that's when, and more generally, if your G is a torus, so it's like C star M, an algebraic torus of dimension M, then the classifying space of this torus is just the product of the classifying space of each component. So it's a So the is a product of M copies of CP infinity. Yeah, actually, we will mostly just consider this case. But now let's go back to a more general setting. So more general setting. So here, let's be general. So G is some Lie group and X is topological space, and we have a continuous map of G on X on the left. And we can, so here we have EG cross X over EG. So this is like trivial fiber bundle of fiber X over EG. And then, so EG, so we know that the GX freely on the right on EG. And let's it acts on the product in the following way. So EX dot A is E dot A inverse dot X. So recall that the G action on X is on the left, this inverse make it a right action. And then this action is free because it's already free in EG. So now the horizontal lines are principal G bundles. And then this, after we quotient by the trivial, the free G action, we get this, usually non-trivial principal fiber bundle over BG with fiber X. So this X sub G is this. So when the G action on X is free, this is, because EG is contrable, this is homotopic to S, the quotient of X by G. So equivariant cohomology, like in the free action case, it's just the cohomology of the quotient. But in general, so in general, this is the definition of G equivariant cohomology in topology. So the G equivariant cohomology of X, where X is equipped with some left G action, with any coefficient ring, it's just by definition this X sub G. And also so this X sub G over BG, the classifying space of G. This is a fiber bundle with fiber X. So we consider a fiber X. So now this inclusion map called I induces a map between cohomology. So there's a map from the equivariant cohomology to the usual cohomology. And this inclusion, because all the inclusion from different fiber are homotopy equivalent or homotopic to each other, so they induce the same map. Sometimes we will call this map like taking the non-equivariant limit. Okay, so that's a brief review of G equivariant cohomology. So let's go back to Gromov-Witten theory. Suppose that everything now is like X is a complex projective manifold, and then we have complex algebraic group G acting on X, and it induces G action. Recall that the last time, like we have a virtual fundamental class, and we have the virtual tangent bundle. It turns out that this G can be So the G action can be lifted to this virtual tangent bundle on the moduli space. And now, so recall that the bottom line is we can think this virtual fundamental class integrating against the virtual fundamental class gives a map from like virtual push forward to a point. So it decreased the degree of the cohomology by 2 times the virtual dimension, which is the degree of the virtual fundamental class. And this is Q linear. But then here, I mean, here, this is just the cohomology of a point. So the cohomology of a point is like 0 if degree is not 0. So 0 is like 1-dimensional. So that's the like bottom row. But then on the top, we have the equivariant version. So now it's like G equivariant cohomology of the moduli of stable maps. So when we have this G action on X, we have this G equivariant push forward. So the target of this so it's defined by some G equivariant version of the virtual fundamental class. And it decreased the degree by 2 times the virtual dimension. But now this is like more interesting. So we will actually specialize to the case that G is a torus. So if we have now let's see gamma I tilde are G equivariant cohomology classes on X with rational coefficient. And we have non-negative integers A1 to AN. So now we define this G equivariant G equivariant descendant Gromov-Witten invariants by the same formula. It's just we replace, so now gamma I are G equivariant classes. Psi are actually now also G equivariant cohomology classes, and we use the G equivariant virtual push forward to a point. We get an element in the G equivariant cohomology of a point, or equivalently the cohomology of the classifying space BG of G. Okay, so now, I will, so now suppose that our G is a torus of dimension M. And as we have seen, the classing phi space is just M copy of CP infinity. Then the so the cohomology ring of the BT is just a polynomial ring generated by M variables U1 to UM, and there are second cohomology classes. Basically, it's like the pullback of C1 of O minus 1 on each CP infinity. So it's just a polynomial ring. So you see when it's in this, when G is the torus, so then now, this can, you see then this can have any positive degree. And moreover, in this case, so here in this case, the top, so maybe let me go to the next page. So this invariant, so we know when T is this torus, so this equivariant Gromov-Witten, T equivariant Gromov-Witten invariants, so they are polynomials in U1 to UM. And to recover the non-equivariant version, basically it's evaluated as 0. So this is so finally, okay, so after I finish this virtual localization, I'll take a break. Okay, so yes. So the equivariant, so the advantage of like considering the like equivariant version of Gromov-Witten invariants. So the first thing is it's one of the most important tools to compute Gromov-Witten invariants. So this is virtual, but so let me recall the virtual localization proved by Graeber, Panda, and Kai-Barent. So it's a virtual version of a TIA-bot localization formula. So let's code curly, let's call this m bar gn x beta curly x or fixed gn beta. So recall that already there's some fundamental, so there are like virtual, I think, let me just, so recall that last time, so this is this virtual tangent bundle is the difference of two vector bundles. But then now in the G equivalent case, E1 and E0 and E1 are G equivalent. So let's just focus on the like the case where the group is a torus. So these are T equivalent vector bundles. So now suppose that, so we have this is the, so this is the fixed, so this is a T fix. Yeah, in this case, a substack is a closed substack. So then if you so then if we restrict to this so if we restrict I from 0 to 1, so this is our T equivalent vector, with restrict to the fixed locus. So maybe let's see, like in general, TX is let's say we have some, so it's a disjoint union of connected components. So say it's like labeled by some graph. So this is a so this is a, oh, so each is a substack of xt. Yeah, so usually actually we will make them connected components, but sometimes F gamma it's convenient to, like F gamma can be a union of connected components. So we have this. Now if we restrict EI to each of this F gamma, right? So then Tx on the fiber, so it is decomposed into the fixed part and the moving part. So yeah, actually, let me say on the whole xt. And so this EI so the T virtual of the fixed point is the fixed part. So the restriction of the virtual yeah, let me see. So when we restrict the virtual tangent bundle of the whole thing to the torus fixed part, and the fixed part gives us the virtual tangent bundle of the torus fixed part. And this can have like different dimension for different component F gamma. And the moving part gives us the virtual normal bundle. And then we have so let me just write it as N virtual. So these are T equivariant vector bundles. Okay, so now with this notation, we are ready to state the localization formula. So if we have an equivariant cohomology class alpha, and we pair it with the virtual fundamental class, so this will give us the equivariant cohomology of a point, which is a polynomial ring in the which is polynomial in UIs. And this can be computed by this formula. So we restrict this. So I is the inclusion. Or maybe I just say, oh, I alpha. So I is the inclusion of the torus fixed stack 2x. And so this equivariant Euler class is invertible, or this is just, so we can write it as follows: sum over F, sum over the different component. And now so this has each component, we have this virtual class. And we have yeah, this is the restriction of the virtual normal bundle to the F gamma. Sorry. Okay, so we can compute it, and also we know that we can recover the non-equivariant, the usual Gromov-Witten invariance by the from the equivariant Gromov-Witten invariance. Okay, so finally, this is a useful tool to compute it. And moreover, if X is not proper, but the fixed point is like, so sorry, X is so if the moduli space is not proper, then left-hand side is not defined. But suppose that the T fixed so the moduli space, submoduli space of T fixed stable maps is proper, then the right-hand side is still defined. But but then the left-hand side is not defined, the right-hand side is defined. But now, in general, when the left-hand side is not defined, we will get element in the fractional field. So when the fractional field means you can have like holes in U. So yeah, so you cannot have a non-equivalent limit in general. Yeah, because you oh yeah, I think it is it is a good place to take a break. So after this, I'll start to talk about the algorithm of the topological vertex. Okay, so after so we'll come back. So after this review of the Gromov-Witten theory, which is a mathematical theory of a model topological string theory. Let's specialize to toric Calabi-Yau threefolds. Recall a Calabi-Yau threefold acts as toric if it contains the three-dimensional algebraic torus. So now, from now on, until the end of this talk, capital T will always be C star 3. So X contains C star 3 as an open dense subset, and the action of C star 3 on itself extends to X. So yeah, last week we have seen some example, like most simple example, like C3 O minus 1, the total space of O minus 1 plus O minus 1 over P1, and the total space of O minus 3 over P2 are examples of toric Calabi-Yau threefolds. So we make some assumptions so that the theory is not trivial. We assume that there is at least one fixed point. So the torus fixed point are isolated. We assume there's at least one fixed point. So let's take some point in some fixed point. Then on the fixed point, the torus T acts on the tangent space. And then in particular, it acts on the top exterior power of the tangent space at this point. This is one-dimensional representation, which is not trivial. Which is not trivial, and let T prime be the subtorus, which acts trivially on this complex line. This is called the Calabi-Yau torus. And then this T prime is independent of choice of fixed point because this this line bundle is like dual of the canonical line bundle. It is actually trivial. So let's define a two-dimensional subtorus, which we will call the Calabi-Yau torus, and it's called denoted T prime. So now let X0 is like zero skeleton, is the union of zero-dimensional orbit or torus fixed point. Let X1 be the union of zero-dimensional and one-dimensional orbit. Yeah, let's take some simple example. So for example, if you have two examples. The first example is C3. And so we have the one skeleton is just the zero skeleton is just one fixed point, which is the origin. And the one skeleton is a union of three coordinate axes. And then let's see, union of three coordinate axes. So we would like to, so to use some, graph to specify this configuration of torus invariant lines. So first, so for each C, which is one-dimensional T orbit, which is C, we associated ray. And for each torus fixed point, we associate a vertex. So here we have like 3 T invariant lines. So we have 3 lines. So we have one single trivalent vertex and 3 non-compact edges. But we also want to decorate these edges by the action of the Calabi-Yau torus. So here, so the weight of the tangent weight are like T1, T2, and T1 minus 1, T2 minus 1. Oh. Yes, sorry. So let's look. So the weight are so the weight of the 3 tangent weights at this fixed point are so T1, T2, and T1 minus 1, T2 minus 1. So then we make make this line to be like the line generated by 1, 0, which correspond to T1, 0, 1, which correspond to T2 and minus 1, minus 1. Okay, so this is the toric graph for C3. And let's see. So for the resolved conical, which is a total space of O minus 1 plus O minus 1 over P1. So there are 2 fixed points. So we have this, and we have the one-dimensional T orbit closure is like this P1, which is a 0 section P1. And also, like there are 2 fixed points, and on the fiber at the so the fiber over the 2 fixed point is a copy of C2, and there are 2 torus invariant lines. So we have this configuration of one-dimensional orbit closures. And similarly, so for each P1, we associate the compact line, compact edge. And for each C, we associated array. And for each fixed point, we associate a vertex. We get this trivalent vertex. And again, so this is, so you see like, but basically if you take away the fiber at infinity, you get C3 and you get the graph, toric graph of C3. So now we have another mark point, another torus fixed point, and with the tangent weight given by the other point, the tangent weights are given by T1 inverse, T2 inverse, and T1, T2. And so more generally, if we consider the total space of, so if we want to consider total space a sum of 2 line bundles, the Calabi-Yau condition tells us, the total degree is -2. So it's OM plus OP1 minus M minus 2. So in general, for the first, so P1, there are like 2 fixed points in this total space. At the first fixed point, let W to be the tangent weight to the base P1. And W2 and W3 be the weights at the fiber. So we always have this condition that W1 and W2 will form an integral basis of this character lattice of the Calabi-Yau torus. And W3 is minus W1 minus W2 because the Calabi-Yau torus acts trivially on the, on the top exterior product, so sum is 0. So also the tangent weights, if you have a P1, so the tangent weight at the two fixed points on P1 are the negative of each other. So and then the weights of the other two weights are determined by the degree in the following way. So so if we look at the upper half, so it's the total space of ON over P1 together with the weights. So actually you see that from this planar trivalent graph, we can so we can read of the torus, read of the degrees of the so the splitting type of the normal bundle of this P1, and also together with the action by the clubial torus. So here's an example. So OP2 minus 3. So on the basis P2, and then the base P2, there are 3 projective lines, which are one-dimensional orbits of the torus action. And then we have 3 fixed points, and over each of the three fixed points, the fiber is one-dimensional. So this configuration of rational curves, so we now have 3 P1s, 3 torus fixed points. So we have the toric graph with 3 vertices, 3 compact edges, and 3 non-compact edges. So you see that because for each fixed point, there are always like three edges coming out of it. So it's a trivalent graph. It's locally planar because, for example, if you consider this graph of OP2 minus 3, and if you remove one of the fixed points, say the top vertex, so this corresponds to you remove the fiber at infinity. Fiber at one of the fixed point in P2, fiber at the point. So then after you remove that fiber, what you get is the total space of O minus 3, the bottom part. So this part will give you the total space of, so this is O minus 3 plus. So actually we can compare this with this picture. So this is actually, this will be O1 plus OP1 minus 3. So this part will be this. So we see that if we take away this and we take the toric graph of this, and these 2 edges will eventually intersect. So we want to think it not as in the plane, embedded in a plane, just like locally planar. Oh, I hope this is clear. So you see, like in general, for every toric clubial threefold, you can look at this one skeleton and the action of the clubial torus at a fixed point, and you can draw this graph. Okay. So let me first describe so the algorithm of proposed by Agnagich, Clem-Marino, and Vafa topological vertex, as I mentioned last week, is based on the large N duality relating topological string on clubial threefolds and Chern-Simon gate 3 on 3 real manifolds. So this is what they propose. So they propose that there exists open Gromov-Witten invariants. So what do they count? So they So consider C3, and we have this L1, L2, and L3. They are Lagrangian submanifold, which is diffeomorphic to circle times C. And they intersect, so they're L1, L2, L3. L1 intersect the first axis and not the other two. And it bounds the embedded holomorphic disk D1 in the Z1 axis. So this open invariance should count holomorphic maps from border Riemann surface sigma. So it can have any number of handles and any number of boundary circles. So the boundary circles are mapped to the union of the three Lagrangian submanifolds. So we can say like Rij is R1J is mapped to the first Lagrangian L1 and so on. Yeah, so it's this. So now, so yeah, I think last time there was some question. You see now the degree of the map will become some relative homology class. But because it's C3, so actually this relative homology class of the map is completely determined by, you consider the boundary and yeah, each of the boundary circles. So the boundary circle Rij under U is pushed forward. It will, so the Rij is represents some first homology, the first homology class, and then this will be a first homology class in Li. But this Li, the first homology, Li is homotopic to a circle. And so the class is just generated by the boundary of Di. So then it's some multiple of the boundary of Di, and because it's like because this map is holomorphic, and then the boundary of Di is oriented by the complex structure on the disk Di. So this will be some positive, so this will be some positive numbers. So we call them winding numbers. So yeah, so these are I described, so at least so there are some maps. So there should, they predict there we should be able to do virtual count of such holomorphic maps. So one can compute the virtual dimension. It's always 0 for any genus and any winding numbers. So you see, we can collect all these winding numbers in 3 groups associated to L1, L2, and L3, and we get 3 partitions, mu1, mu2, and mu3. So you see that the topological type, so then the length of these partitions tells you how many boundary circles there are. So the topological type of the domain and the topological type of the map is determined by this genus G and these three partitions. But unlike the closed Gromov-Witten invariant, for open Gromov-Witten invariants, so this is not, it's usually not well defined because the moduli space is, in the best case, it's orbifold with corners. So we need to specify, to do intersection theory on some manifold with some, actually, it's a manifold with boundary, then we need to specify some boundary condition, and the boundary condition is specified by 3 integers. And actually this invariance will depend on the choice of the 3 integers. So Ni is called the framing of Li. So now, yeah, so this FG mu n is the generating so now it's so these are Gromov, so yeah, so this FG mu n is, we need to fix this framing to get well-defined numbers. And if we fix G and fix 3 partitions, we should get a number, right? Which are virtual count, which is the virtual count of a holomorphic map with this Lagrangian boundary conditions, with this genus and this winding numbers. So now for the to match it with the Chen-Simon invariance, so we will fix the winding numbers and sum over the genus. And also yeah, so this C is some, so this should be N. So it's some generating function of some disconnected version of the invariance that we just described. So the second thing is that, so Gromov-Witten invariance of any toric-Calabi-Yau threefold can be expressed in terms of this open Gromov-Witten invariance of C3. So the idea is the any toric-Calabi-Yau threefold can be obtained by gluing C3s, one copy of C3 for each the torus fixed point. And then the gluing axiom saying that we have this generating function of open Gromov-Witten invariance for each copy of C3, and the Gromov-Witten invariance of the whole thing can be obtained by gluing this generating function of open Gromov-Witten invariance. Okay, and finally, yeah, it's most interesting. Yeah, it's actually, they actually provide a closed formula of this generating function, which is pretty amazing, with sum over 3 partitions. So if we fix 3 partitions, like fix collection of winding numbers and fix this framing, then yeah, then sum over the genus, they provide a closed formula. So here, and also the framing dependence is easy like this. And then this W is, yeah, they get this by using large N dualities obtained by you take the color Humfley polynomial of a particular link with 3 components, and then they get all this. And then yeah, at first, so but the thing is, yeah, so now it's an old story, it's 20 years ago, but when this prediction first appeared, it's really surprising. Yes, and then no, I still remember like the first time, like, yeah, so we heard about this, that there's some things that so the Lagrangian is like 3-dimensional. It doesn't split the 6-dimensional Calabi-Yau into 2 pieces. So how can you get this? Yeah, how can you do this? So we actually develop, so let me say, so we develop a mathematical theory. So this is also, so Zhenli, Kefeng Liu, Jianzhou, and myself. So we develop mathematical theory of the topological vertex based on relative Gromov-Witten theory and degeneration formula. So so corresponding to their O1, O2, and O3. So let me first give you a summary. So we define formal relative Gromov-Witten invariance of relative formal toric-Calabi-Yau threefolds. These invariants are refinements and generalizations of Gromov-Witten invariance of smooth toric-Calabi-Yau threefolds. Formal relative Gromov-Witten invariants satisfy the degeneration formula. So they can be they can be expressed in terms of C. So now we have the C tilde, which is now we define it as a formal relative Gromov-Witten invariance of decomposable relative formal toric Calabi-Yau threefold. So finally, we also have a combinatorial expression for our C tilde. It has the same framing dependence. And W tilde is in terms of representation of symmetric groups. So okay, at the end of the day, yeah, C tilde will be equal to C and W tilde will be equal to W. Yeah, so this is all, but I also want to say that so there are like recent work by Norman Doe and Brad Parker, and called the topological vertex. And it's topological vertex in terms of relative Gromov-Witten invariance of log club EL and enumeration of tropical curves. So yeah, so this is still like pretty recent work, very much related to this topological vertex. Okay, so the idea is the following. So recall that we take a X and we produce this planar trivalent graph gamma X. And then actually from this planar trivalent graph, we can reproduce a formal T-equivalent formal neighborhood of the one skeleton in X. So T-equivalent formal neighborhood of this like union of 0 and 1 dimensional orbits of the torus action. And when we compute the Gromov-Witten invariance by localized, so no, actually it's not compute, because you see in general, if we take arbitrary X and any curve class, since our target X is a non-compact, so this virtual fundamental class, yeah, it's the moduli space can be non-compact. We have seen there in some cases moduli space is compact, and this invariant can be defined. But in general, but in general, so suppose it's defined, then we can compute by localization. Oh, so this is sum over connected components. But then in general, this is not defined, but we use this to define the invariance. So now what is the formal toric-Labial graphs? So our theory is a generalization. So we define formal toric-Labial graph is a generalization of this, which is a generalization of this. So if we start with this graph, so first thing is for each non-compact H, so yeah, the picture is this. So for each non-compact H, we make it compact by like replace the end by a univalent vertex. So in the picture here is before compactification, we have a P1 corresponding to this compact H, and then this is, so adding a univalent vertex correspond to, we compactify the C by adding a point at infinity we call D1. But then this configuration, we should think this is not so what we are going to construct is some formal toric-Labial threefold. So it's a three-dimensional thing. So we should also know when we compactify the C with C1, we need to specify the normal bundle. And we want it to be log-Labial. So this D1 in this picture is a point, but it's really you should think this like we have a copy of C2 and we take the formal neighborhood of the origin. This is a component of divisor D hat. So if corresponding so in order to have the normal bound splitting, so then because of the formal Torrey-Calabi-Yau condition, the degree of the normal bundle will have of C1 is -1, and we need to specify the splitting is given by some integer. So it's ON1 plus O minus N1 minus 1. So now the thing is so now you see that, so to specify this degrees together with the Calabi-Yau torus action, we put the framing vector F1 and minus F1. So if you look at this part, so from here we can read off the normal bundle of C1 in the whole thing together with the torus action. And we do similarly for each of this. So this is a generalization is for each non-compact edge, non-compact edge, we add a univalent vertex together with this framing vector. The framing vector is determining some integers. So this will correspond to the framing of the Lagrangian. So we replace the Lagrangian. So in the original picture, this is that they put the Lagrangian on this leg, but instead we compactify it and we get a divisor. And the framing of the Lagrangian in our setup will be like the splitting of normal bundle. And now so just by generalizing, so you see that this generalize this. And if we generalize this construction, we will get this relative formal Torrey-Calabi-Yau threefold. And so this data is enough for us to define and compute invariants by localization. So we call them formal relative Gromov-Witten invariants. So we need to specify the degree, and we also need to specify the ramification pattern. So that's one generalization we generalize, so we add these divisors, which will correspond to the Lagrangian boundary condition. And we also want to introduce like nodal singularities. We want to degenerate. So that's if we add so this corresponds if we had the compact edge, we can introduce a bivalent vertex. So the picture is the following. So this corresponds to, we degenerate this P1 into two P1s. But recall that we also want this slide. So now we get something with normal crossing singularity. But when we split this, so we also need to, because what we want to construct is the formal threefolds. So we need to know how the normal bundle of the original C0 split into the two pieces. So originally, the C0 has the splitting N0 and minus N0 minus 2. So after we degenerate, so the first N0 is split into degree A on the left-hand side and degree B on the right-hand side. And the second factor, minus N0 minus 2, is split into a minus A minus 1 minus B minus 1. So the log Calabi-Yau or relative Calabi-Yau condition tells us the degree of the normal bundle of C0 prime and C0 double prime, is -2. And then, so we need to, so then the framing vector will tell us this splitting together with the action of the Calabi-Yau torus. Okay, so we have, so now we can actually define invariance also for this kind of a slightly singular target. So now we have the degeneration formula. So the idea is just simple. So if we have a bivalent vertex, so which correspond to this picture, we can get rid of this, this singularity by two ways. So first, we can smooth it. So this corresponds to the operation of the graph. You just remove this bivalent vertex and forget about the framing here. And the other way is resolve it. Yeah, it's just separated and we get this. So now the degeneration formula relate the formal relative Gromov-Witten invariance of the smoothing and the resolution. So if we have some relative stable maps to this target, and when we degenerate, so then it's split into two, the stable maps into two, this target correspond to gamma 1 and gamma 2. But then the ramification of the two sides must be equal. Conversely, if we have a pair of relative stable maps such that the ramification in the middle is equal, we can we can glue it and smooth it. So as you can see, so it's even if you have a curve with connected domain, after you do this, you might get a disconnected domain on one side. So it's more convenient to just allow disconnected domain so that the gluing formula will be simpler. Yeah, so this is the so this is exactly the gluing formula. So if we have degree D, so we need to specify the degree D of the like degree D of P1, and also the mu1, mu2, mu3, mu4 are 4 partitions. And then the degree to this new curve is determined by the size of the partitions. So so that's the degeneration formula. Does this make sense? So yeah, so yeah, so that's almost I have only 2 more slides. So yeah, so then we see that if you are given any toric labial threefold, we just keep on degenerating. And then then the building block will be like this, right? So this is our replacement of like this open Gromov-Witten invariant of C3. So it will be relative invariant, and it will depend on 3 partitions. And the framing correspond to the splitting of the normal bound of C1, C2, and C3. So we define this and we form generating function. To match the Chern-Simon side, it's convenient to introduce some suitable power of square root of -1. So so this C tilde is this. So this so there's some change of like representation and winding basis. After we make this change, then our invariant defined in terms of formal relative invariant, Gromov-Witten invariant, has the same framing dependence as the C predicted by AKMV. Right, so we compare it with this, right? So, and our gluing formula also coincide with their formula. So it remains to show that our C is equal to their C tilde. And Yeah, so that's the part 3, because they have a combinatorial expression of their C, which is W. And we also have C tilde, which is W tilde. So to finish the proof, we just need to show this is a purely combinatorial problem. And yeah, so my collaborator and I, so Kefeng Liu, Jianzhou, and myself, we can show the case when so first we show the case where only one of the partition is non-empty. Then we show the case when two of the partition is non-empty. So the one leg case correspond to the unknot on the chain segment, and the two leg case correspond to the half link of the chain segment. The unknot case, so there's another proof by Okunkov and Panda. Yeah, so now you see this is like 21 years ago, but we cannot show the 3-leg case. So the 3-leg case actually follows from, the work of, so on open, Gromov-Witten correspondence. But let me first say that the 3-leg case, this identity W is equal to W tilde. So this was finally, proved in 2018. So this finished the mathematical theory. Sorry, may I have, I can actually stop here, or should I? So yeah, maybe so here is some relation between the topological. Okay, so this is the old story. So maybe I think I should stop here, and then next time I will talk about the relationship between this work and the work on Gromov-Witten, Donaldson Thomas by Molly Nekrasov, Okunko, Panda, and others. And Okung. Yeah, and then I will also talk about the generalization to orbifolds.